Hey, hey, it's Dr. J. Today we're going to learn about power functions and polynomials, section 5.2. So let's start off with a power function. The definition of a power function is any function that can be written as f of x, or y if you prefer, equals a times x to the n power. So that's how they get their name. Power functions. N is the power, also known as an exponent. A is called the coefficient. X is, of course, the variable. Sometimes if you Google this, or if you look in a textbook or some kind of textbook, we might say y equals kx to the p. This is another way of expressing a power function. Some people like this version of it. I like the A because I think of A as alpha, and I think of alpha as the leader. That's why it's called alpha, alphabet, things like that. And I like to see A in the front. And so when we write out our equations in this section, I will often go A, B, C, kind of put it in that order. But some people do it this way. You got to be flexible. You don't want to be attached to a particular representation of a function. Instead of f, you could call it y. Instead of a, you can call it k. I'll teach you guys a little German today. The German word for constant is constant. It just starts with the letter k. And then p for power. So if you prefer this version of it, y equals kx to the p, you certainly are more than welcome to use that version of it. But in my lectures, I typically use this version of it. Although I think you've already seen me several times this semester interchange f of x and y whenever I feel the need to. Okay. And typically, n, the power, is greater than or equal to 1. Yeah. Or in this case, if you're using the letter p, you could say p is greater than or equal to 1. Otherwise, it wouldn't be a power function. It would be either a constant function or a reciprocal function, which we'll be discussing. I guess we've already discussed constants and reciprocals, so we will not be discussing them in this lecture. Okay, so that's the definition of a power function. Let's go ahead and take a look at what they look like. Let's start off with a equal to 1. So it will be invisible. So we'll have f of x is just x to the n. So our leading coefficient is just 1. If you like to put the 1, you certainly can, but it becomes very annoying if every time you have to write a power function of this form that you have to put that invisible 1 there. So it's up to you. Sometimes I put it, sometimes I don't. All right, so let's just take a look at what these functions look like. So if we have f of x equals x to the 1 power, that would just be a straight line. Okay. Now, we've already had an entire lesson on transformations and graphing functions and making tables of values. For practical purposes, if I start going down that road in this lecture, we will never get out of here. So I'm just going to do my graphs very quickly. If you need to refer back to your old notes to see how I drew that line, you can get all into that later. So we've got f of x is equal to x squared. So I'm going through all the different possible power functions. X squared is a parabola. Okay. X cubed So basically what I'm doing is I'm allowing n to change. You know, here we have n equals 1. Here we have n equals 2. Here we have n equals 3. So on and so forth. Okay. You all recognize this one? This is called the cubic. So all of these were done previously. Although I don't think we got much farther than that. That's about it. So the next one would be called the quartic. I always think of a quart of milk, or a quarter of a dollar. So it's called quartic. Yeah, fourth power. This graph looks very much like a parabola. It just has a sort of a flatter bottom. So it's very difficult to tell these two apart. The only difference, or the main difference, is that when you get down here on the x-axis, it's much flatter. It's much closer to the x-axis. I could spend an hour going into why that's true. When you plug in the values of x and you raise them to the fourth power, it shrinks them down because these values are less than 1. So all the values between -1 and 1 get compressed. They get shrunk down very small because you're raising them to the fourth power. Again, I'm not going to go all into that or we'll never get out of here. All right. This spot's not very useful. Let's do x to the 5th. This is called the quintic, or la quinta. The quintic looks much like the cubic. So this is called the quintic. Yeah. And again, by the same argument, in the cubic, it's sort of a smooth curve. And in this one, it's the same smooth sort of S-shaped curve, but it's flatter as you get towards the origin. I'm only going to do a couple more of these, and I think you'll see the pattern. I hope you'll see the pattern. So the next one is the 6th power, called the sextick. I think we'll stop at the 7th power. The sextick looks a lot like the quartic. It's just even flatter. So as the power gets larger, this sort of base down here along the x-axis gets very, very flat. Now, I know in my drawing it looks like it's touching, but if you zoomed in on it, it would only touch at this one point called the vertex. Okay. Let's do one more. It's called the septic, x to the 7th. And you can just imagine the pattern continues. After this, it would be the 8th power and the 9th power and so on and so forth. So the septic looks a lot like the quintic. It's just flatter still. And again, it might look like it's touching more than once, but it is only touching one point. This point is called the inflection point. So odd powers have inflection points. Even powers have vertices. Or you can just say vertex if there's only one. If there's more than one, then you have to say vertices. Okay, so odd powers have inflections. Even powers have vertices. Okay. Now, technically, the linear function is a power function. Yeah, it is technically a power function. But since the power is 1, it does not have a vertex or an inflection point. It has neither. So there's no vertex or inflection. It's just every point is equivalent to every other point on the linear function. We won't be studying linear functions very often. In fact, hardly at all. Most of the problems that we will be doing in this section will be at least the very minimum x to the 2nd power. But I didn't want to boot this one out of the family because technically it's a power function. It's like, hey, I have a power. It's 1, that counts. That's a power. Some people even include 0 as a power, but I'm not going to go there because if the power is 0, then it's not really a power. Okay, so the smallest power that makes sense in this context is 1. All right. And so what we're going to learn in this section, other than the shapes of the graphs, is we are going to pay attention to the arrows. What direction are these arrows going? And this is called the end behavior. Now again, arrows are not a mathematical term. There's no definition in math of what an arrow is. So you know what I mean. Arrows, the tip, the end of the graph. I think I've mentioned this in previous lessons that the arrows really don't exist anyway. It's just we're human beings and our minds like to say, hey, you're going that way. And so we put a little arrow tip on it to indicate direction. But we all know that in reality, these graphs actually look like that. The arrows are not actually there. But don't the graphs look so boring without the arrows on them? It's hard to tell what's going on. So we like to put the arrows so you can tell which way you're going. Yeah, like on a street. You put a little arrow, say one way go this way and one way go the other way. You don't have to have the arrows, but it certainly helps. So the direction of these arrows is called the end behavior. And there's a very precise way to write the end behavior. Okay? So let's just take the linear function here, for example. All right, we always start with the left-hand arrow. Always start with the left-hand arrow. And you're going to say, as x approaches negative infinity, that's the left hand, comma, the function f of x, well, what's happening to this function here? What's happening to the direction of the arrow? The direction of the arrow is going down to negative infinity. So we say as x approaches, so this arrow is read as the word approaches. That's what this arrow means. So we say as x approaches negative infinity, f of x is approaching negative infinity. All right. That's the left side. For the right side, which way is x going? X is going to positive infinity, or you can just say infinity, comma, what's happening to the arrow? As x goes to infinity, the f of x, or if you like, you can just say y. I'm using the function notation. F of x is approaching infinity. And so this is what we call the end behavior. It's as if we're ignoring everything in here. All right, you're ignoring the middle, and you're only looking at what's happening at, we call this the end of the day. Right? At the end of the day, what's happening to the function? Ignore the middle part of the day. Right? So let's go through all of these. Now that you see the notation, we can sort of go through them quickly. I'm going to need this space, so let's just do these ones, and then I'll do some more problems. Okay? Well, obviously, that's all we're doing today. So. Problems, problems, problems. But remember, not every problem has to be a problem. So let's look. We start with the left end. So you say, as x approaches negative infinity. So x is going towards negative infinity. What's happening to the arrow? F of x is going to positive infinity. See? Positive infinity. For the right end, as x approaches positive infinity, so x is going to the right, well, f of x is still going to positive infinity. Okay. That's the end behavior. And we can go through all of these. You're going to notice that there's a pattern. It won't take very long to discover. Look at the... You're ignoring the middle anyway, right? So look. If you're ignoring the middle, look. The cubic... Remember, this was x cubed. I don't know why I erased those. This one's x squared. Yeah. This one's just x. Or x to the 1. So when you're ignoring everything that's in the middle, this function has the same end behavior as the linear function. In fact, all the odd powers will look like the linear. Yeah, they'll all have the same right arrow goes up, left arrow goes down. So you already have your end behavior. You did it over here with the linear function. As x approaches negative infinity, f of x is approaching negative infinity. Yeah, same thing it was over here. And then as x approaches positive infinity, f of x approaches positive infinity. Okay. And then it's probably not a big surprise. This one was what? The quartic, x to the 4th. X to the 4th, both arrows point up. That's exactly the same as x to the 2nd. So it's going to be the same thing for x to the 4th. As x approaches negative infinity, comma. The comma is kind of necessary, so it reads like a sentence. As x approaches negative infinity, take a breath, f of x, well, where's it going? F of x is going up to positive infinity. In fact, they're both going to go up. So for the right-hand side, you say as x approaches positive infinity, f of x also approaches positive infinity. So I would just memorize odd power, even power, odd power, even power. And now you don't have to do the rest of them. If you said f of x was x to the 5th, it would be the same as same end behavior as x to the 3rd, which we just did right here. Or the same as x. And then if you want to go higher, x to the 6th, well, that's an even power, so that would be the same end behavior as x to the 4th and x to the 2nd, and so on and so forth. Now remember, this is the simplest case where the coefficient is 1. All right, that's not going to last very long. The coefficient is going to change in my next example. Well, actually, this is just the definition. Let's actually do an example now. So I guess we'll call this example 1. I want to start numbering now that I'm done with the welcome message. Welcome to end behavior. Welcome to the end. So example 1, determine the end behavior. Let's do a couple different ones. All right. So, in reality, it's very rare that the constant, the leading coefficient, would be 1. I mean, it could happen once, maybe. But then after that, once you get into the deep end, that's not going to happen anymore. So this is a leading coefficient here of -1. Yeah. So there's a -1 right here. Some people actually like to put it just so that it's not invisible. If you're like that, you like to see every element of the function, then by all means, write it. Okay, so what's happening here? This is a reflection about the x-axis. So you're going to take this graph, x to the 5th. Yeah, this would just be x to the 5th. And you're going to flip it over the x-axis. Yeah. So you're going to flip it over the x-axis. So this part of the graph is going to get flipped down here. And this part's going to get flipped up here. Yeah. So this is now the graph of -1 times x to the 5th. Now again, you could go back to chapter 3 and you could make an XY chart and you could plot a bunch of points. It's going to take you a lot of time. In this chapter, we're not graphing like that. We're using experiential graphing, so we know what this looks like from past experience. I don't want to go relive all that over again. Do you? You really want to do all that? You can if you must. I mean, if you don't have any other way to do it, then please make a table and plot all the points and then multiply them all by -1, and then this is what you're going to get. So here is your now finished graph here. Again, all we care about is the end behavior. Always start with the left end. Okay, so you're going to say as x approaches -infinity, what's happening to f of x? F of x is approaching, we're looking at the left end. F of x is approaching +infinity. It's going up. Okay. Then we go to the right end. As x approaches +infinity, what's happening to the y? Remember, f is the same as y. The direction is going down. And there you go. There's your end behavior. Okay. So we got 3 times x to the 4th. Let's just look at the mother function x to the 4th, which we already did. So this would just be x to the 4th. All right. And then we're going to scale or stretch vertically by a factor of 3. Okay. So what's that going to do to the graph? It's just going to make it tall and skinny. That's all it's going to do. It's just going to stretch the graph out vertically like this, like taffy. You know, just took a nice chunk of it and stretched it out vertically. But notice the arrows don't change. So when you're multiplying by a constant that's positive, Since the scalar, that's what that's called, the scalar or the constant or the leading coefficient, it's got lots of different names. Since the scalar is positive, the arrows are going to go in exactly the same direction. All right, so the green is our actual graph. That's the graph of all of this. Okay, and remember, we are ignoring everything except the arrows. So we're going to say as x goes to negative infinity, what's happening to the y, or in this case it's called g. G is going to positive infinity. It's going up. Now we go to the right end of town, or the east end of town. As x goes to positive infinity, what's happening to g of x? On the right side, it is still going up. So that's your answer for part B. Here's part A. And scrunch down here in the corner, I've got my part C. I mention this a lot, and you're probably getting sick of me saying it, but anytime you have a function, you could just rewrite the function notation as y, and it's a lot easier to work with. It's a lot easier to plug and plot and solve and everything like that. Just remember that it still is a function. If you rewrite it, it doesn't change its functionality. It's just changing what you're calling it. Okay. Tomato, tomato, right? All right, this time we have a negative scalar, so that's going to reflect and stretch. Now remember, the stretching, like in the last example, the stretching doesn't do much, right? Stretching, independent of other factors, doesn't change much. It's the reflecting that you got to be careful about. So look at the mother function. X to the 6, that's our mother function. X to the 6 looks almost exactly like x to the 4th, right? All the even power functions look like parabolas. Yeah? They just get flatter and flatter and flatter and flatter at the bottom. You might wonder, well, what does x to the 100th look like? Yeah, we'll talk about that later. It looks like almost like a box. It's so square. I said we'd talk about it later, and here I am talking about it now. Okay, so we're going to flip this thing over the x-axis and stretch. Now again, if you want to do it the hard way, the chapter 3 way, where we make a table, you make a table of x's and y's, and then you would multiply all the y's by -2, and then all the y's would go upside down. But this is basically what you're going to end up with. You're going to end up with a graph that looks a little skinnier than this. It's been stretched out, and it's upside down. Yeah, and it still kind of has a flat base here. Although I'm not really grading your graphs in this section, 5.2. So if you can do all these problems without drawing a graph, maybe you have a really good imagination and you can just look at the equation, close your eyes, and picture the graph in your head, then all of this can just simply be done with mental math. All right, these are just your little clouds of what you're imagining if you're good at imagining graphs. If you're not good at imagining graphs, that's fine. It's a skill. It takes time. And that's what we're here for. Yeah, one thing at a time. All right, so all we care about is the end. The end behavior is the arrows. Both arrows are pointing down. I just need to make some room for my answer. So here is my graph that I'm looking at. Both arrows are pointing down. So we say as x goes to -infinity, well, y is going to -infinity. It's going down. As x goes to +infinity, y is still going down. Y is going to negative infinity. Okay. Now, some people like recipes. And recipes are not a bad idea, especially if you want to be able to quickly reproduce an effect or an answer, a result, right? You don't want to have to go and make it from scratch. I mean, I would like you to know how to make it from scratch. Ideally, you learn mathematics, and then if you forget a formula, because that often happens, my running joke is I have forgotten more formulas than I currently know, because when you get to be my age, you've learned hundreds of thousands, if not millions of different formulas, and there's no human being that I know that can remember that much stuff. So if you forget a formula, then you can cook it up from scratch. If you happen to know the formula or the recipe, then you don't have to cook it up from scratch, okay? So there are 4 possibilities. There are only 4 possible end behaviors. All right. And they depend on the value of the constant and on the value of the power. So you have f of x is a x to the n. If a is positive and n is even, then both arrows go up. For simplicity, I'm just using the letter y. It means the same thing as f. All right, so that's one possibility. Yeah. The second possibility. A is negative, n is even. So you have a negative constant, and you have a even power. Well, we just did this, right? If the constant is negative and the power is even, both arrows go down. There you go. So you have a quick way of looking at it. Is it negative constant, even power? Boom, there's your answer. If you know the recipe. If you don't know the recipe, then you have to cook it up from scratch. All right, third possibility. A is positive, n is odd. So if a is positive and n is odd, well, then the right arrow goes up and the left arrow goes down. I always do the left one first. This is exactly like the linear function that I did, the straight line, yeah, because straight line is definitely odd, yeah, with a positive leading coefficient. And then your final possibility, well, there's only one thing left, right? A is negative, less than 0, and n is odd. All right, and there's only one possibility left, so what does it have to be? It has to be the one we haven't done yet. So as x goes to negative infinity, y goes to positive infinity. Look at the pattern. That's the only one that's not there yet. And then as x goes to infinity, y goes down to negative infinity. So if you're good at memorizing recipes, or if you just want to make yourself a little cheat sheet that just has these 4 possibilities, it'll make it so that you can go through the homework, or you can go through the test, quiz, lab, whatever, and have, instant satisfaction. Okay, so those are the power functions. It's so pretty, isn't it? I just don't want to erase it. Take a good look at it. Let me screen save it because it's going bye-bye. So another name for power function is a monomial. A monomial, yeah, it's just another name for a power function. So I have 3 monomials here. Okay. If we add them together, we get a polynomial. So you have monomial, monomial, monomial. If we add them together, everything is considered adding, even if it's negative. But nobody wants to write this, including myself, and I really love math, and I still don't want to write plus parentheses, minus parentheses. That's just too much. So we typically rewrite it like this. And this is called a polynomial. Okay. So a polynomial has some important terminology. The largest power is called the degree. It's called the degree of the polynomial. So we call this a third degree polynomial, or degree 3. The number in front of the largest power the variable, I'm abbreviating here, I'm leaving out some words, of the variable with the largest power is called, well, largest, it's in the front, it's the leader. So we're going to call it the leading coefficient. Sometimes when I'm talking really fast, or when I'm, in a pinch for time, or if it's not really, important in that problem, it's just a passing word, I might say leader. I'll say, look at the leader. It's just easier than saying leading coefficient. Sometimes I'll say leader. So we have the degree, and we have the leading coefficient. So, x-intercepts. X-intercepts, where it crosses the x-axis, they're also called real zeros. There is a slight distinction that I will make at some point when it becomes important, but for this particular introduction to polynomials, I can say x-intercept, or I could say real zero, and I essentially mean the same thing. Okay. So we have a theorem. It's called the real zeros theorem. A polynomial of degree n has at most n real zeros. So this particular polynomial has at most n real zeros. So what does that mean? That means that it could cross one time the x-axis. It could cross two times. Again, I'm only concerned with the x-axis right here. We'll talk about the y-intercepts later. Or it could cross three times. But this polynomial could never cross more than three times. So it's at most whatever the degree is. If the degree is 3, it could cross once, it could cross twice, or it could cross three times. This particular one is actually this one. Yeah. It crosses three times. I'm not going to get into the details. I'm just talking about the theorem. You can think of a theorem. We're not spending a huge amount of time with theorems, but a theorem is a fact that has already been proven by your ancestors. So you don't have to prove it unless you want to go to graduate school, become a math major, and then you start proving theorems. In this class, theorems are just taken as like the law of gravity or something. It was proven. You don't have to worry about it. All right, this is a fact. You never even have to solve a theorem. You just use it. You say, there's a theorem that says that this must be true. Okay, it's true. Okay. So let's do some more examples. Determine the degree. The leading coefficient. And the maximum number of real zeros. We only emphasize the word real because there are imaginary zeros. We learned about those in chapter 2. We won't be graphing imaginary zeros, so since we are only concerned with the graphs, we're only concerned with the real zeros. Come back to me. Give it a second. Wow. Whoever invented autofocus, I hate you. I've tried to turn it off and it still happens. So come on, come back. Or maybe it'll come up while I'm writing down the problem. So we'll do A. Say f of x is 3x squared minus 5x to the 4th plus 6x minus 2. B, I guess they can all be called f. There's nothing wrong with that. Negative x to the 5th plus 3x to the 4th minus 7x cubed plus 2x squared plus 5x. I don't know. Well, that's enough. And C, I got room for a part C here. F of x is I guess I really don't need another one, do I? What the heck. 4x to the 3rd plus x squared minus 6x plus 7. Okay, so determine the degree, the leading coefficient, and the maximum number of zeros. So the degree is the largest power. Sometimes we like to write it in standard order, although the word is not standard, it's actually descending order. Fancy way to say it is descending powers order. Largest power, then second largest power, so on and so forth. Sometimes there will be some powers that don't occur. So for example, there's no cubic in this one. All right. So then we have the degree is 3. The leading coefficient is -5. I'm going to abbreviate coef. Or you could just say leader. Like if you're taking notes very quickly, you want to say leader, leading coefficient. That L didn't look right. There we go. Leading coefficient, and then the maximum number of zeros. It's just the same as the degree. So really, you get 2 for the price of 1 here if you remember the theorem. You know, the degree is always equal to the maximum number of real zeros. Okay, this one's already in descending order. Yeah, in fact, the next 2 are already in descending order. I just like to start off by pointing that out. If you see a problem that's not in descending order, I recommend rewriting it in descending order. Highly recommend it. Although I can't really require it at this point. If there comes a time where I want to require it, then I will not recommend it. I will require it. Right now, it's a recommendation. There's an invisible -1 right here. Yeah, so we got degree 5, leading coefficient, or I can just say leader, -1. Again, leader is not the proper word. It's leading coefficient, also known as leader. And then the max number of zeros is the same as the degree, 5. I feel silly. I'm so glad I caught this before I have to award somebody extra credit here. So stop the tape. I circled the 4. And then by the time my hand went over here, I wrote 3. You know what I meant, right? I said 4, right? There's the degree. I know I got a lot of extra credit eyes out there watching, trying to get that point. You know, not this time, kids. I caught it. So degree 4, maximum number of zeros is 4. All right, now this one is degree 3. So degree 3, it's already in descending order. Leading coefficient is 4. And the max number of zeros is 3. I'm so glad I caught that. You know, I'm trying to save. I only got a finite number of extra credit points that I could give out, you know, so I don't want to give them all out today. So, still got a couple more weeks to find them. So, all right, that's it. Degree, leading coefficient, maximum number of real zeros. So what is the difference between a 0 and an x-intercept? It's just a tiny little bit. An x-intercept is an ordered pair. It's an ordered pair that always has a number and then 0. Yeah, the second coordinate is always 0. But the question mark here could be any real number. Doesn't necessarily have to be 0. It might be 0, but it could be -5. It could be 2.5. It could be the square root of 5. It could be anything, any real number. Okay? Does that look like a number? I'm just going to write the word number. I think it's easier. Sometimes I use the hashtag, and it's like, I think that hashtag has gotten a different meaning in the last 10 years or so. Okay. A 0 I'll make sure I don't go out of camera range, is just the x coordinate. So x equals whatever this value is. So it is a matter of, semantics. When I say x-intercept, do I really mean real 0? Yeah, I do. I mean that. But if I say find the x-intercept, then you have to write it as a pair. If I say real 0, you just tell me the x. So for example, I don't know, I'm not going to get too far into this, but suppose I got a function that goes like this. Yeah. So what are the, and let's give them some numbers. Let's call this 2. Let's call this -3, 4, 5, and -6. Okay. So I would say the x-intercepts, you have to do pairs. -6, 0. -3, 0. 2, 0. Now, again, I'm skipping all the steps on how I got the graph. That's for a later lesson. In this lesson, I've already done the graph. And then real zeros, you simply list out the x's. -6, -3, 2. And you don't use any parentheses or brackets or braces or anything like that. It is just a list of the x-coordinate or the x-coordinates if they're more than one, and ordered pairs if there are more than one. All right, so that's very important vocabulary, because when I put the problem on the test, and if I ask for intercepts and you give me zeros, I mean, I know what you mean, and I'm like, oh, I know that you knew it, but I want you to know it, right? So if I ask for this, then give me this, If I ask for real zeros, then give me this, and it's going to be very important on the test, okay? All right, well, let's do some. Let's find some problems. Ready? Let's solve some problems. I already found them all. I got to solve them now. Example 3. Find the x-intercepts. You do not have to draw the graph. I mean, if you want to, or if you, maybe I will just for fun, because I like this stuff, but you don't have to. You just have to solve it. So f of x is x cubed plus 11x squared plus 28x. Okay. So what you're going to do is, this is actually y. In fact, one thing you can do when you're doing your homework is, when you see it on the screen as f, write it on paper as y. And then you save yourself that one step. Okay. For an x-intercept, y is always 0. That's what an x-intercept is. Y is always 0, so you're going to set this equal to 0. Or if you prefer, maybe you're right-handed, sometimes we put the 0 on the right-hand side. It doesn't really matter. Tomato, tomato means the same thing. This is a cubic, so you need to somehow factor it down to make it smaller. So let's pull out a common x. If necessary, use the quadratic formula, only if it's absolutely necessary. If you can get away without doing it, then please save yourself the suffering and try to do it without the quadratic formula. So 7 times 4 is 28. Oh, and it's also 11. When you add 7 plus 4, you get 11. So I'm glad I didn't spend 10 minutes on the quadratic formula there. If you can't factor it in 1 minute, or maybe 2 tops, I wouldn't spend more than 2 minutes, then go ahead and use the formula. At that point, the formula will be faster. Okay. All right. And now you're going to set these all equal to 0. That's a free answer right there. You could probably do these all in your head. God, I hope you could do these in your head. X plus 4 is equal to 0. X equals -4. All right, this is college algebra. It's not beginning algebra where although sometimes I show steps that I know that you already know, and I hope you know that I know that you know. Okay. So these are the real zeros, but the question is, what are the x-intercepts? So the x-intercepts are 0, 0, -7, 0, and -4, 0. Those are your x-intercepts. Okay. And maybe I'll make a note. The real zeros are, and you just list them out, 0, -7, and -4. And I don't even care what order you list them in. Some people are really picky about the order. There might be a reason why somebody would be picky about the order. If we were graphing, or if we were doing inequalities or sign testing, any of these other things that the order matters, but the order doesn't matter here. Okay? And if you're not sure whether the order matters, well, then just put it in order. And then, you can't lose that way, right? Okay. How about example 4? List the real zeros. By the way, by saying list, I'm really giving you a hint that it's just going to be a list of numbers, not a set of points. A very common name for a polynomial is P of x. Polynomial in x. P of x. Polynomial in x. Okay. All right. So the real zeros, again, you are going to set the equation equal to 0. And it doesn't matter what side you put the 0 on. Now here's one thing I want to make sure you don't do. Don't put 0 inside. What you're doing is you're basically replacing this with y, and then you're saying y is equal to 0. That's what you're saying. You're not saying that x is 0. All right, we'll get to that in a second. But right now we're saying that y is equal to 0. All right, look for something they have in common. They're both divisible by 3. And you can take out a square. Yeah, x squared can come out. So remember, factoring mentally is the same as dividing, right? So you're saying 3x to the fourth divided by 3x to the second, well, that leaves you with x to the second left. Yeah. And you could easily check, notice I'm using my finger and not the pen, you can easily check 3x squared times x squared. You could double check that that's 3x to the fourth. All right. And then now 27x squared, or actually negative 27x squared, divided by 3x squared is 9, or in particular, negative 9. All right. And then again, do a quick double check. 3x squared, x squared, that'll be x to the fourth. 3x squared, negative 9, that'll be negative 27x squared. Okay, keep going. You can't do anything with that. That's already done, but you can break this one up. X minus 3, x plus 3. Remember that special factorization from beginning algebra where you learned how to separate the difference of two squares. This only works if the constant is a perfect square and it must be a subtraction difference. Okay. And so now you're going to get 3x squared equals 0, or x minus 3 equals 0, or x plus 3 equals 0. Divide by 3, you're going to get x squared is equal to 0. Take the square root, you're going to get x is equal to 0. Sometimes people just jump right to here. That's fine. You could just jump from here and go whoop, all the way to here and say x is equal to 0. And I hope you can jump these ones too. X minus 3 becomes 3. X plus 3 becomes negative 3. All right. And so list the real zeros. The answer is x equals 0, 3, and negative 3. Just list them all out. No parentheses, no brackets, no braces, none of that stuff. Let's do another one. I should mention, look how many zeros there are. There's only 3. Look what the degree was. 4. Yeah. So going back, reflecting back on a previous example, I said there was a theorem that says the maximum number of real zeros was 4. Yeah, that's the maximum number. Doesn't mean you're going to get what the max guarantees. It's just saying you're not going to get more than 4. Well, we didn't get more than 4. We got 3 real zeros, which is less than the maximum. We could have gotten 4, but we didn't. We got 3. Example 5. Find all real zeros. 7x cubed plus 5x squared minus 112x minus 80. I haven't been drawing the graphs for these. Maybe on this one, because it's kind of an elaborate one, I'll show you a little picture of what it looks like. The section 5.3 coming soon will show all the graphs. You're going to see all this again with a focus on what the picture looks like. Okay. Let's just cut to the chase. Find all real zeros. That means that we're setting this equal to 0. Remember, don't plug in 0, but set it equal to 0. You know, you can leave the 0 on the left-hand side. I mean, there's nothing wrong with that. There are left-handed people in the world, right? So this is what we call factor by grouping. we always cut it right down the middle and make sure that you don't chop off this minus sign here. So you want to make sure you keep that minus sign in group 2. All right. If you accidentally chop off the minus sign and put the minus sign with group 1, it screws everything all up. There are examples, elaborate ones, that have to be really cooked up in advance where you have to reshuffle the groups, but I didn't make any of those because I'm just trying to cut to the vocabulary, to the concept, and not too much, suffering. So I always made it group 1 is the first 2, group 2 is the second 2, but you do need to be careful with that minus sign. So group 1, when you factor them, you can only pull out an x squared. Okay. Group 2, when you factor them, what's the largest number that goes into both of these? Can you see what it is? Yeah, 16. Yeah. Maybe you can't see that, but 16 is the largest number. 16 goes into 80 5 times, and 16 goes into 112 7 times. Look, that's not a coincidence. Yeah. If this is a 7, then that has to be a 7 also. In fact, it's 7x. Yeah. Now here's the weird part. This negative and this negative factor out, and then you have to change the sign to a positive. All right. And you could think about that logically, or you could just memorize it. A negative times a positive is a negative 80. Yeah. So if you screw up and you accidentally leave that negative, there are 2 red flags. One red flag is these aren't the same. That's a huge red flag. These should be the same. The other red flag is a negative times a negative would be a positive 80, and that's not a positive 80. Yeah. Now, if that was a positive 80, then this would be correct, but it's not. So there it is now. Okay. Now, when you do grouping, you take the common group and you write it only once. All right, only once. I go into this in my, if some of you have had my basic algebra class or my intermediate algebra class, I spend a lot of time on this concept because sometimes the human brain will think, oh, I've got one, I've got another one, I want to put a 2 over here. Sometimes people will put a 2, or sometimes people put a 2 right there. You don't do that. That's just not the way factoring works. I could have 20 of these factors, and when I pulled it out to the front, you would write it only once. And then I like to cross it off. Some instructors think I'm kind of babying you when I do that, because you don't really need to cross it off. Why am I babying you? Well, it helps, I think. I mean, anything that you don't have to see is a little bit easier. So then just take down what we call the leftovers. X squared minus 16. Oh, there's that recipe again. Special sauce. Has to be a difference, and it has to be a perfect square. One of them's minus, the other one's plus. It doesn't matter which, as long as you have one of each. Okay. Set these all equal to 0. I'm doing it left-handed here. These are easy. I'm not even showing the math on that one. Maybe I'll show the math on this one because this one's a little trickier. You're going to subtract 5. And then you're going to divide 7. Divide by 7. I don't know if you can see that. That's a negative 5/7. Just to blow that up down there. All right. So those are the real zeros. Negative 5/7, 4, and negative 4. So if we were graphing, I would probably want them in order. So let's say 1, 2, 3, 4. 1, 2, 3, -4. So on the graph, they would have to be in the right order. -5/7 is about right here. Yeah. It's almost a half. It's actually a little bit to the left of a half. Yeah. 5/10 would be a half, so that's 5/7. So it's between 0 and -1. If this is -1, this is 0, it's kind of in the middle. On homework or something like that, as long as it's in the middle, you don't have to be, as long as you're close. Obviously, I'm not going to be able to tell whether it's 5/7 or not, right? The graphing from this point out is a little bit, hit and miss, okay? And so this would look like a graph that goes like this. And then, again, this is just FYI for your information. It's not that I'm asking for this in this chapter, or in this section of the chapter. In 5.3, I will be asking, we will revisit this in section 5.3. Okay, I think I have time for one more. Let's do one more. Let's do example 6. Find the x-intercepts, the y-intercept, and the end behavior. All right, so we haven't talked about the y-intercept. Let's do that first, because it's easy. Just plug in x equals 0. All right, earlier I had said don't plug in 0 because that was for the x-intercepts. For the y-intercept, it's actually very easy. It's just plugging in 0. So you're just going to put 0 in for x. And see what you get. You got 0. So the y-intercept is 0, 0. All right, that's essentially a free answer. All right, you never have to work very hard for the y-intercept. You just have to remember what to do. All right. For the x-intercepts, that's where you actually have to do the work. You set it equal to 0 and do exactly what we did in the last problem. Factor it out. If you get desperate, you can use the quadratic formula. You're going to get x equals 0, x equals 4, and x equals -3. Yeah, mental math. If you don't want to do mental math, then you can take these equations and solve them like I did in the other problems. I'm coming to the end of our time today, so I'm going to go ahead and move on. So the x-intercepts, plural. Y-intercept is always singular. There's always only one. But x-intercepts, you might have many. 0, 0, 4, 0. Make sure you put it in the right order. Breaks my heart when you get the answer right and then the computer marks it wrong because you typed it in incorrectly. And then you might make a mental note. 0, 0 is both. Okay, and then finally for the end behavior, look at the leader for the end behavior. When you're finding the end behavior, all that matters is the leading term or the leader. So it's x cubed. Yeah, you can ignore all of the other terms when you're finding the end behavior. All right, so we have x to the third. So that would be, we got the recipe, right? The leader is positive, the power is odd. So as x goes to negative infinity, y goes to negative infinity. As x goes to infinity, y goes to infinity. That's your end behavior. I'm going to talk a little bit more about end behavior in part 2 of this lecture. Until next time, this is Dr. Jordan signing out.